Hello and welcome to the Autodidact Scientist Algorithm series, where I will be giving you an intuitive insight into a variety of algorithms that are used in machine learning. I'm your host, Rich Gregson, and before we get started, I would greatly appreciate it if you would like this video and subscribe to our channel. So the algorithm that we're going to cover today is naive Bayes. So what is a naive Bayes? The Bayes theorem is the foundation of the probabilistic machine learning method known as the naive Bayes, and naive Bayes is utilized for a variety of classification problems. Now, it's a fantastic illustration of how the most straightforward answers are frequently the most effective. Despite the recent developments in machine learning, naive Bayes have shown to be not only quick, it's accurate and dependable, but it's also very simple. And it's been used successfully for many things, but it specifically excels at solving natural language processing issues. Okay, so before we jump into the naive Bayes, let's understand what Bayes' theorem is. So for estimating conditional probabilities, the Bayes theorem is a straightforward mathematical formula. So given that another event has already occurred and we know this by assumption, presumption, statement, or any other supporting evidence, conditional probability measures the likelihood that another event will also occur. So the formula for Bayes' theorem is on screen at the moment, and PAB on the left hand side is the posterior probability, how often A happens given that B happens. PA is the prior probability, and that is how likely A is to happen on its own. PBA is the likelihood, and that's how often B happens given that A happens. And PB is the marginal probability, so that's how likely B is to happen on its own. In simpler terms, the Bayes theorem is a way of finding a probability of when something happens when we know certain other probabilities of other events. So what are prior and posterior probabilities? The posterior probability is also known as the Bayesian posterior probability, is on the left-hand side of the equation. The prior probability, also known as the Bayesian prior probability, is on the right of the equation, and it's modified by the data you gather about occurrences A and occurrences B separately. Now, according to the definition, the likelihood that an event A will occur given the knowledge we have about event B is the same as the likelihood that event B will occur given the knowledge we have about event A, modified by the knowledge we have about those events A and B separately from one another. And based on the evidence, which is usually the data you've gathered, you might conceive of this as having a prior probability, the guess or the Bayesian prior, and the posterior probability is the improved guess. So let's talk about the naive Bayes then. What are the assumptions of a naive Bayes? Now, the core premise of a naive Bayes is that each characteristic contributes equally and independently to the target result. So to gain a better understanding, let's use a small example. Car theft. So the data set you can see on screen basically says whether a car has been stolen or it hasn't. And the criteria that we have is the color, type, origin, and we've got a list of the example number assigned to these particular observations. Now, the algorithm's assumptions can be understood in relation to our data set as that we presume that there are no dependent feature pairs. So, for instance, that the fact that the car is red has nothing to do with its type or origin. So as a result, it's presumed that the features are independent of each other. Second, each attribute receives the same amount of weight or importance. So for instance, it's impossible to accurately forecast the outcome with only color and origin. Therefore, it's considered that all of these traits are relevant and contribute equally to the target outcome. So given the characteristics of the car in our dataset, we must categorize the vehicle if it's stolen. These features are represented by columns, whereas the individual items are represented by rows. So the car is stolen if the color is red, the type is sports, and the origin is domestic, as seen in the dataset's first row. Therefore, what we're going to do now is determine whether a red domestic SUV is being stolen or not. Notably, in our data collection, we don't have a single instance of a red domestic SUV. So, according to this example, Bayes' theorem can be rewritten as the first equation you can see on screen on the right. The variable y is the class variable, which represents if the car is stolen or not, given the conditions, and variable x represents the parameters or features contained within the dataset. The formula of x is the second one down on screen. So here x1, x2, or x to the power of n represents the features, i.e. they can be mapped to color, type, and origin. And by substituting for x and expanding it using the chain rule, we get the third equation on screen. Now, you may look at the data set to get the values for each and enter them into the equation. But the denominator does not vary for any of the entries into the data set. It's a constant. So as a result, proportionality can be introduced without using the denominator, and this gives the fourth equation on screen. So in that equation, the class variable y in our example only has two possibilities, which are yes or no. And there may be in circumstances where the classification is multivariate, and as a result, we need to identify the class variable y with the highest likelihood. Given the predictors, we can get the class using the y function you can see, which is the last equation on screen. So now it is possible to get the posterior probability in this example, PYX, by first building a frequency table that compares each attribute to the target. The posterior probability for each class is then calculated using the naive Bayesian equation. After converting the frequency tables into likelihood tables, the result of the prediction is the class with the highest posterior probability, and the frequency and the likelihood tables for each of these three predictors are also shown here. So you've got the color, you've got the type, and you've got the origin. So in our example, we have three predictors denoted as X. So as the equations we discussed earlier, we can calculate the posterior probability as P yes X, as shown in the top part of this particular slide, and we can calculate the P no X, as shown as the second part. So since 0.144 is greater than 0.048, this means given the features red, SUV, and domestic, our example gets classified as no. No, the car is not stolen. Okay, so for those of you who are mathematically inclined, you may have noticed one drawback of the naive Bayes, and that is the frequency-based probability estimate will be zero if there are no instances of a class label and a specific attribute value together. And so when all these probabilities are multiplied, this will result in a zero. So when an attribute value doesn't appear with every class value, you can add a 1 to the count for each attribute value class combination as a solution to this problem in a Bayesian context. And this problem is called the zero frequency problem. So, for example, say your training data set looks like what's in the top right hand corner. We should then add 1 to every value in this table when you're using it to calculate probabilities, and it will result in the table in the bottom right. And this is one of many ways of how to get rid of calculating a zero probability. What are the types of naive Bayes classifier? The first one is multinomial, and the multinomial frequency distribution of certain occurrences are represented by feature vectors. And this particular model is the one most frequently employed for document classification. The second is Bernoulli, and the features are separate Booleans, binary variables, that independently describe inputs in the multivariate Bernoulli event model. Now, this paradigm is common for document classification problems where binary term occurrence features, that is, whether a word appears in a document or not, are utilized rather than the term's frequencies. The next one is a Gaussian naive Bayes classifier. In Gaussian naive Bayes, it's assumed that each feature's continuous values are distributed according to Gaussian distribution or a normal distribution. As illustrated in the graph you can see just under the text on screen. When plotted, it yields a bell-shaped curve that's symmetric about the mean of the feature values. Okay, we've got a couple of considerations of what we need to do with our data and when to use a naive Bayes classifier. So your categorical inputs, your label qualities like binary, categorical, or nominal are already presupposed by naive Bayes. Your Gaussian inputs, a Gaussian distribution is taken into account if the input variables have actual values. If your data's univariate distributions are Gaussian or close to Gaussian, the method will operate much more effectively. This might necessitate deleting outliers, so values that are more than 3 or 4 standard deviations from the mean. Your classification problems, the naive Bayes algorithm is appropriate for binary and multi-class classification. Your log probabilities, in order to calculate the probability of various class values, many small numbers must be multiplied together. So this can result in a lack of numerical precision. In order to prevent this underflow, it's recommended that you employ a log transform of the probabilities. The kernel functions, so more complex distributions, including various kernel density functions, can be utilized for numerical input values instead of assuming that they will have Gaussian distribution. And update your probabilities. You can easily adjust your model's probabilities when fresh data becomes available. If your data changes regularly, the naive Bayes will be useful. So what are the advantages and disadvantages of naive Bayes? So let's start with the advantages, of course. Naive Bayes can accurately estimate the class of a test data set, and it operates relatively quickly. It can be used to resolve multi-class prediction issues because it works well with multi-class predictions. And if the independence of a feature is true, the naive Bayes classifier performs better than other models with less training data. And also, if you have a categorical input variable, the naive Bayes algorithm performs exceptionally better in comparison when it's working with numerical variables. A couple of the disadvantages, as previously discussed, the naive Bayes model will give can give a zero probability and won't be able to make any predictions. If your test data set doesn't contain a categorical variable of a particular category that wasn't present in the training data set, so you'll have to employ some sort of smoothing approach to address this. I've already given you one method of that already. The algorithm, naive Bayes algorithm, is infamous for being quite a bad estimator. So you shouldn't take the probability outputs of the predict prober method too seriously. And also, it makes the assumption that each feature is independent. Although, that seems like a wonderful idea in principle, you hardly ever discover a group of independent qualities in real life practice. And that concludes this video on naive Bayes. Now, I hope this video helped you get an idea of how it works and when to use it. And if you've got any questions, comments, or feedback, please contact me personally through my social media channels or through the Autodidact social media channels. Also, another reminder, please support us and like the video, share the video, and subscribe to our channel. Thanks for watching.